Alright, so I've got a graph of a rational function here, and the function is y equals 2x plus 3 over x minus 2. So this is a rational function because it's the ratio of two polynomials, polynomial divided by another. And rational functions have some interesting properties. So, for example, like what the heck's going on with this thing? The function's going along, and all of a sudden there's this crazy vertical line. Very strange. Well, actually, this vertical line is not part of the graph. My graphing tool drew that there because it got very confused. Why would it get confused? Okay, so this is called a vertical asymptote. And it did that because it got confused, which I'll explain in a second. Another strange thing, or interesting, or fun thing about this rational function is that as it goes this way, as x approaches positive infinity, the function seems to be heading towards a certain line here. And then likewise, as I approach negative infinity, as x approaches negative infinity, the value of the function also seems to be heading towards this line. Okay? Well, that line which it seems to be heading towards as it goes, towards positive infinity or towards negative infinity, is called a horizontal asymptote. So there's vertical and horizontal asymptotes. Okay, so what would cause a function to be confused, or a grapher to be confused and to draw this strange vertical line, which really shouldn't be there? Well, look at the denominator of this rational function, x minus 2. What happens if x equals 2? I would get 2 minus 2, which is 0. And if you divide by 0, the universe explodes. You can't do that. More mildly speaking, the function is not defined at x equals 2. So there's a hole at x is 2. It's undefined there. And not only is there a hole there, it has no value when x is 2. There's actually a vertical asymptote. So it's this vertical line, which is the line x equals 2. Sorry, I should. So this line is actually x equals 2. See, here's 2. It's not part of the graph though. It shouldn't really show up on the graph, but graphers do that because they get confused. So what we should really do is draw kind of like a dotted line to show that maybe if we were graphing this by hand, it would be a helpful tool to sort of sketch this vertical asymptote, but it's not part of the graph itself because the function is undefined at x equals 2. So that's a vertical asymptote. So not only does the graph have no value at x equals 2, but there's also this line, this vertical line, which it does not ever cross. Okay, so a function cannot cross or pass through a vertical asymptote. Well, okay, so in some functions there'll be, just a hole at a certain value. That's a hole. And some functions there'll actually be, alright, this is not accurate at all, but there will actually be this like kind of line you can imagine. Okay, that's terrible. Back up. Okay, sometimes there'll be just a hole where the function is not defined, and then sometimes there'll be this dramatic like avoidance of this vertical line, right? And that vertical line is called a vertical asymptote. So how do you tell when there's just a hole? If there's a value for x for which the denominator is 0, there's definitely going to be some kind of problem. There's going to be a hole, or there's going to be a vertical asymptote. Some kind of issue because you can't divide by 0. How do you tell whether it's just a hole or whether there's actually a vertical asymptote? Well, here's the rule. If the factor x minus a, so for example, in this case, x minus 2, x minus some number, occurs more times in the denominator than the numerator, So there's no factor x minus 2 up here in the numerator. So it happens one time in this denominator and 0 times in the numerator. So it happens more often in the denominator. Then the graph will have a vertical asymptote at x equals a. So in this case, this factor x minus 2 occurs more times in the denominator than the numerator, and that means that there is a vertical asymptote at x equals 2. Now if this function were 2x plus 3 and then there's x minus 2, like that, and you could expand that, or whatever. If we had a factor of 2x plus 3 and x minus 2, this factor would occur one time in the numerator and one time in the denominator. So this condition would not hold. So then there would just be a hole at x minus 2. You still couldn't have a value at x equals 2. Sorry, there'd still be a hole at x equals 2, positive 2. Because 2 would make the denominator 0, and that's illegal. So there'd still be a hole there. There just wouldn't be a vertical asymptote. Okay. Now, a horizontal asymptote is a little less dramatic than a vertical asymptote because a function is allowed to cross it. It could. There's no. The universe doesn't explode if it touches the horizontal asymptote, as if it were to touch the vertical asymptote. It's more like, it's just a horizontal asymptote is just something about the behavior of the graph. As it goes this way, it approaches a certain line. As it goes this way, it approaches that same line. Not every rational function will have a horizontal asymptote. It could have 0 horizontal asymptotes. It could have a lot of horizontal asymptotes. How do you determine if there is one? Well, one, you could just graph it and look and see if it seems to approach a certain line as the values of x get really large and really small. Or you can determine algebraically if the numerator and denominator of a rational function are polynomials of the same degree. So in this case, our example, each of these polynomials was a first degree polynomial, meaning the highest degree is 1. So we have 2x to the first here. It's the highest degree. You can imagine there's like a x to the 0 here, 3x to the 0. That's the next lowest term. But if the highest term is the same degree in the top polynomial and the bottom polynomial, then there will be a horizontal asymptote at y equals, and then the quotient of the leading coefficients. So here, okay. So these are both first degree polynomials, and the term with the highest degree on the top is 2x, and the term with the highest degree on the bottom is just this x. You can imagine that as like a 1x maybe. So 2x to the first, we could call that 1x to the first. So 2 and 1 are the leading coefficients. So we just take the quotient of the leading coefficients. So we'd have a horizontal asymptote at y equals 2 over 1, also known as y equals 2, which is where this line, again, it's not part of the graph, but that's where the horizontal asymptote is showing itself. So something like that. And if you were to kind of zoom out your graph so you can look farther and farther this way and farther that way, you'd see that these lines would get closer and closer and closer to that line of y equals 2. Y equals 2. Alright, so let's do some examples here and figure out if there's vertical asymptotes, and if so, where, and if there's horizontal asymptotes, and if so, where. Okay. So let's look at vertical asymptotes first. So we want to figure out what values of x would cause the denominator to equal 0. So we've got a second degree polynomial here, and so we can do like we do when we're solving quadratic equations. We could factor this. So we could have x plus 3 x plus 2, because 3 times 2 is 6 and 3 plus 2 is 5. So we've got Okay, so we've got these factors. Um, and do we have either one of those factors in the numerator? No, there's not really a way I can factor the numerator to get, x plus 3 times something or x plus 2 times something. So both of these factors occur more times in the denominator than the numerator. So we've got a vertical asymptote called a VA at x equals -3 and x equals -2. Because -3 is the value that would cause this to be 0. -3 plus 3 is 0. -2 is the value that would cause this to be 0. -2 plus 2 is -2. Or you could, think of this as if the factor x minus a occurs more times in the denominator than the numerator, blah blah blah. X plus 3, you could look at that as x minus minus 3. So a would be -3. Okay. So that's where the vertical asymptotes are. There's two of them. One's at x equals -3, so it'd be like a vertical line here. But again, the line wouldn't be part of the graph. It'd be kind of an invisible part of the graph, unless the grapher gets confused and does like a crazy vertical line, but it's not supposed to. So the vertical asymptotes would be at -3 and -2, so here and here. And let's look at horizontal asymptotes. So if the numerator and denominator of a rational function are polynomials of the same degree, which they are, the other rule is if the degree of the denominator is higher than the degree of the numerator, then just the horizontal asymptote is the x-axis. In this case, we are both these polynomials are second-degree polynomials. So the leading term of the numerator is -7, because -7x squared is the term with the highest degree. The leading term here is 1x squared. So same degree, same degree. So our horizontal asymptote would be at y equals -7. So it'd be like down here somewhere. So as the x values get closer to positive infinity and closer to negative infinity, they will seem to approach this line of y equals -7. All right, let's try this one. Vertical asymptotes. So let's factor the bottom. So we could call that x times 3, and here's why. We could factor the top too. We could factor an x out of the top, so x times 3. So x times 2x is 2x squared. X times 1 is x. In other words, x times 2x plus 1 would be 2x squared plus x. So this factor of x occurs once in the denominator and once in the numerator. So in other words, it doesn't occur more often in the denominator than the numerator. So there wouldn't be a vertical asymptote at x equals 0. But there would be a hole at x equals 0. Because 0, so if, 3 times 0 would be 0, and then the function would be undefined. So it'd be a little hole at x equals 0. So I guess we could say the domain of this function would be x not equal to 0. Like, that's not allowed. Okay, what about horizontal asymptotes? So here, this is a second degree polynomial because the term with the highest degree is a second degree term. It's just 2x raised to the power of 2. Here we have a first degree. So if the degree of the denominator is higher than the degree of the numerator, then the x-axis is a horizontal asymptote. Well, here the numerator has a higher degree polynomial. Okay, so that doesn't apply. The numerator and denominator don't have the same degree of polynomial, so that doesn't apply. So no horizontal asymptote here. So that's fine. Doesn't have to have one. All right, let's do one more. We got y equals x plus 2 and an x squared plus 6x over x squared plus 6x. Sorry, y equals x plus 2 over x squared plus 6x plus 8. So let's check for vertical asymptotes first. So we could factor the bottom and figure out where this could be 0. So we want them to multiply to 8 and add to 6, so x plus 4, x plus 2. So the function is definitely undefined at x is -4 and -2, but is there a vertical asymptote at those places? Well, this factor x plus 2 occurs once in the denominator and once in the numerator, so so there would be no vertical asymptote at x equals -2. But there would be a vertical asymptote at x equals -4, because that factor x plus 4 doesn't occur in the numerator at all. So vertical asymptote is x equals -4. Now horizontal, here's the condition that would apply here. So if the degree of the denominator is higher than the degree of the numerator, then the x-axis is the horizontal asymptote. So here, this is the highest term is raised to the power of 2. Here, the highest term is raised to the power of 1. So this polynomial here is a higher degree polynomial than the numerator. So the horizontal asymptote will just be y equals 0, the x-axis.